There's a place in Canada where Earth pulls on you less, and the reason why goes deeper than the Ice Age. Earth feels familiar, solid, predictable, steady beneath our feet. But hidden inside this planet are subtle fingerprints left behind by ice, rock, and deep time, and one of the clearest fingerprints lies across northern Canada. Here, stretching over the land surrounding Hudson Bay, scientists have detected a measurable dip in Earth's gravity. Not enough for a human to notice, but enough for satellites in orbit to detect from hundreds of kilometers above. It looks like a gravitational dent on the map, a quiet anomaly in one of the most remote regions on the continent. This is the Hudson Bay gravity anomaly, and to understand why it exists, we have to follow the forces that shaped this land long before humans ever arrived. Most people think of gravity as constant, an unchanging pull that's the same everywhere. But gravity depends on mass. The more mass beneath your feet, the stronger the gravitational pull. The less mass, the weaker it becomes. And across Hudson Bay, satellites measure noticeably less pull than expected. For a person, the difference is tiny. Someone weighing 150 pounds elsewhere would weigh roughly 149.992 here, a difference too small for even a precise scale to detect. But to scientists, this subtle decrease means something important. Something either removed mass from the region, or prevented mass from returning. And to understand what that something was, we need to go back to the last ice age. 20,000 years ago, Canada was crushed beneath the Laurentide ice sheet, a slab of ice up to 3 kilometers thick and so heavy it bent Earth's crust downward like a loaded spring. Under that unimaginable weight, the land sank. When the ice age ended and the ice slowly melted away, the pressure lifted, but the crust didn't instantly rise back to its original position. Instead, it began a slow, steady rebound, something called glacial isostatic adjustment. Even today, long after the ice disappeared, Hudson Bay is still rising by several millimeters every year as the crust recovers. But it hasn't fully risen yet. It remains lower and lighter than it once was, and that incomplete rebound explains part of the gravity anomaly. But only part. For decades, many believed the ice age alone caused the anomaly. But satellite measurements showed the story was more complex. Scientists turned to seismic waves to look deeper into the mantle beneath Canada, and discovered an even larger piece of the puzzle. A region of mantle material that is lower in density than the mantle around it. It's not visible from the surface, but gravity feels this difference. The most accepted explanation is mantle convection, the slow, looping movement of hot rock rising and cooler rock sinking. Over millions of years, this process redistributed mass under North America, creating a subtle but significant reduction in mantle density beneath Hudson Bay. When combined with the land still rebounding from the Ice Age, the two effects together form one of the clearest gravity anomalies on Earth. A two-layered memory etched into the crust and mantle. Understanding this anomaly in detail required extraordinary tools. The breakthrough came from NASA's GRACE mission, two satellites orbiting Earth one behind the other. Instead of looking downward, they watched each other, measuring their separation with microscopic precision. When the lead satellite passed over an area of stronger gravity, it accelerated slightly, stretching the distance between the pair. When gravity weakened beneath them, the distance contracted. These tiny changes, millimeters at most, allowed scientists to map Earth's gravity field in unprecedented detail. And on that map, one feature stood out. A deep blue depression centered on Hudson Bay, perfectly outlining the region affected by ancient ice and unusual mantle structure. It was one of the clearest signals ever recorded by the mission. For everyday life, this difference in gravity doesn't affect people. You won't feel lighter or notice anything unusual. But scientifically, the anomaly is incredibly valuable. It reveals how continents respond after massive ice sheets melt. It reveals how mantle material moves and shifts beneath our feet. And it shows that gravity is not a constant at all, but a dynamic field shaped by the invisible architecture inside our planet. Small differences in gravity tell big stories about Earth's interior and its past. One of the most fascinating parts of this story is that Hudson Bay is still rising. The crust continues to rebound upward, slowly restoring the mass that was lost when the enormous ice sheet melted. Permanent GPS stations anchored into the bedrock measure this movement year after year, tracking a landscape still adjusting to events that ended thousands of years ago. Over the next several millennia, this uplift will alter coastlines, shift drainage patterns, and gradually reduce the strength of the gravity anomaly. What satellites see today is not permanent, it's part of an ongoing geological recovery. The land holds the memory of the Ice Age, and that memory is fading very slowly as the crust rises and the mantle settles. The Hudson Bay gravity anomaly is more than a scientific curiosity. It's a geological time capsule, a window into the forces that carved a continent, the flows deep within the mantle, and the weight of an ice sheet long gone. Gravity may feel constant, but it carries the history of Earth within it, a record written not on the surface, but deep in the layers beneath us. And as the land continues to rise and the mantle continues to adjust, even this anomaly will gradually disappear. Earth is full of hidden stories like this, stories preserved in its gravity, in its rocks, and in the quiet motions of the crust. If you want to explore more of the real mysteries shaping our planet, subscribe to Atlas Unfiltered, and join me as we uncover the stories the Earth is still trying to tell.